construction of random functions. And we have 3 talks. So first talk is unbiasable verifiable random functions. And the speaker is Emmanuel Ginta. Okay, so please start.
Okay, slides. Okay, just try. Okay, so welcome everyone. I'm Emanuele Giunta, and today I'm going to present our work on unbiasable verifiable random functions. It is joint work with Alistair Stewart from Web3 Foundation. So first of all, let me start reminding what is a VRF. So a VRF is essentially the public key version of a pseudo-random function. We have key generation, evaluation, and verification algorithms. And essentially, we have one party which can at first generate keys, in particular a verification key and an evaluation secret key. Next, any other external user can ask for an input to evaluate the VRF on. And given this input, is it possible to use the secret evaluation key to evaluate the VRF on this input and obtain the unique output associated to it, along with a proof. Now, this is verifiable, so of course it is possible to publicly verify that the output is correct using the proof and the verification key. Now, the 2 key properties we want VRF to satisfy, according to the original definition at least, are uniqueness and pseudo-randomness, along with correctness. Uniqueness asks that no matter how the key was generated, there must be only one output for every possible input. While pseudo-randomness asks that for points that were not really evaluated yet, the output has to be pseudo-random, or at least computationally indistinguishable from random. So to discuss about application of VRF, let me start with an example that was first mentioned to me by my co-author, Alistair. There is a toy protocol that is Poker VRF. So you want to make a card game out of VRF. So to make this example application, let's suppose we have several users who want to play poker. And they first begin by putting on the table one verification key, each generating its own, and secretly keeping the evaluation key. Now, every time we want a user to draw one card from the deck, we somehow generate a random input. This could be coming from a random oracle hashing some public state, or trusted party, or coin tossing protocols, whatever works. So there is a random input all parties agree on, and everybody can evaluate locally their own VRF on this random input that is public. Every party gets one VRF output that is private until they decide to publish it. And whenever they want to play their own card, they just publish the output along with the proof of the VRF. Now, this essentially allows you to build whatever card games you have in mind, satisfying unpredictability in the sense that you cannot guess other parties' card, unless you collude. But it fails to satisfy fairness, meaning that certain parties can augment their own probability of winning the game by choosing maliciously the verification keys associated to them. Now, this actually comes in 2 flavors of possible attacks. The first attack is simply one user choosing one verification key that allows him to get more often than the others cards that are winning, for instance, high-value cards. Another possible attacking scenario is for 2 different parties colluding and generating verification keys that produce correlated outputs. So in this case, for instance, 2 parties can collude and generate 2 malicious verification keys that give the same output every time. Now, this, of course, is an issue for many problems, and this is actually just a metaphor, if you want, for a single leader election scheme, where, like, for instance, in blockchain applications, the winner is the one with the highest VRF value. And that is, there are incentives there to try to win the game more often than the other, because you get block rewards. Now, this is a problem that was actually studied before our paper, and there were many proposed solutions for that. The first one that I'm aware of, at least, is UC-VRF, proposed by David and others in 2017. And this actually proposed a very strong security notion for VRF. UC stands for the UC model, so you can imagine. So this is a very strong notion. It implies fairness in the game, as shown before. But unfortunately, it's so strong that you cannot instantiate it without a programmable random oracle. So this is a limitation if you want to have minimal assumptions in your protocol. On the other side, Eskin et al. In 2021 proposed a new definition that we recalled weak unbiasability. That is possible to obtain in the standard model, but unfortunately is not enough to obtain fairness in the protocol I showed before. So I will start by recalling what is the weak unbiasability notion that they provide, and then explaining how to get to our new notion, basically bridging the gap between these two notions. So weak unbiasability essentially is the following game, very simple. At the very beginning, an adversary is asked to give a maliciously generated, potentially, verification key, along with a guess on what the VRF output is going to be on a random point. Next, the challenger is going to actually give this random point, this point x, and the adversary wins if he is able to open his own VRF on this given input, and the output is the one that he guessed at the beginning. So this is essentially asking that the output of the VRF is hard to guess, essentially, without knowing the input. Now, this is already going in the right direction, but unfortunately is not enough to achieve fairness in the previous game for at least two reasons. The first one being that some bits of the output could be biased, even though the output is hard to predict. Essentially, this is true as long as the output space is exponential. You can have these kind of situations. And the second issue is also that this doesn't prevent at all the possibility of creating malicious verification keys that produce correlated outputs. For instance, you can have several keys that are actually the same functions, for instance, and this notion does not prevent it. So to address these second issues first, let's try to tweak this definition towards something that we could use in the game I showed before. So the first attempt would simply be, let's ask the adversary to give many verification keys instead of only one. Now the challenger is going to provide several random points instead of only one, x1, xm. And the adversary now has to open basically all the couples from each verification key in each point provided by the challenger. So essentially has to fill like one table, n by m size, with VRF output and VRF proofs. And we can ask that adversary wins the game as long as basically the proofs are all correct, but the output that you are getting is essentially far from random, far according to some notion, like computationally or statistically. Unfortunately, though, this first attempt does not work for very contrived reasons. And the issue here is we're essentially asking the adversary to break the game to be able to open all these verification keys and hold the domain the VRF are defined. So to make this simple, imagine, for instance, there exists a VRF that is very biased on half of the domain. Like, for instance, it's constant on half of the domain, but in the other half, you are unable to open it because simply the opening proof doesn't exist. Such an adversary would be unable to win this game, but it's still producing a VRF key that is biased, and would be unable to win, by the way, because it's not able to produce this pi ij that is correct. So this definition doesn't really capture all the corner case we need to prove fairness in the previous game. So we need to consider adversaries that are unable to open the VRF in all the points. So let's try to consider this too. And to consider this, we say now, OK, so every time there is a proof that is incorrect, instead of saying, OK, the adversary failed, let's just say we erase the value of this incorrect proof, right? And now we ask, OK, all the non-erased value should be far from random for the adversary to win. Now, this unfortunately also doesn't work, and this is actually much easier to see, and the issue is simply selective opening. Now, let's imagine an adversary that has a VRF that evaluates to 1 or 0. Whenever the output is 1, the adversary gives the right outputs, but whenever it's 0, I just give a wrong proof, and now all the output is suddenly all 1, which is obviously far from random. So this approach also doesn't work. So our final attempt, and this is the final definition, is essentially to ask the adversary to try and bias one specific predicate from a restricted class of predicates, instead of asking for general computational indistinguishability. I will later specify what are the properties of these predicates, but the game now works by asking the adversary to give all this verification key, this predicate P, open all these values. We erase all the values with an incorrect proof, and the adversary wins if the predicate is true. More often than it would be on actual random input Z. So the restriction instead we ask on this predicate to satisfy are for it to be monotone, where in this case monotone means that if the predicate is false on a certain input, erasing certain positions should only make the predicate more false in some sense, but never true. So this is like the thing. So in a maybe more informal way, this is essentially saying that an adversary should not gain any advantage in not opening some VRF value, which is the same in a card game. Like if you don't play a card, you should not be able to win just by not playing it. Okay, so now that we have the definition, I'm going to roughly go through the constructions we have. So we discussed three constructions. One is the folklore transformation from VUF to VRF in the random oracle model. And we will show unbiasability in that setting without programmable random oracle, sorry. Next, we show how to construct in the standard model verifiable random bijection. And afterwards, we provide a compiler from any verifiable random bijection to an unbiasable VRF, starting just from a VRF and basic assumption on pairing groups, on prime order groups and PRFs. So the first step is simply studying the folklore construction from VUF to VRF. And for those who don't know, so a VUF is essentially a verifiable random function, but the output is now asked to be unpredictable instead of pseudo-random for the points we are not opening. Another way of seeing this is just unique signatures for those who are familiar with that object. And the transformation is essentially just hashing the VUF output. So the random oracle is basically transforming something that is unpredictable to something that is actually random. There are two ways of obtaining this transformation. One is hashing all the public information, so the VUF output, the input, and the verification key you have for your VUF. And the second transform is just hashing the outputs, which sounds faster, but usually also less secure. And what we show is that, both are known to be VRF. This is folklore, I would say, at this point. But we also show the first to be essentially unconditionally an unbiasable VUF. An unbiasable VRF for any VUF. Essentially, the reason being that for different input and VK value, essentially, you're hashing different points, so you are expected to get different random values. So there is no way you can meaningfully bias this. The second transform is trickier because you may have 2 points colliding, and this would give the same random value, and that's an issue for unbiasability. So for this reason, you need to ask the VUF to satisfy some weak notion of collision resistance. And in particular, you need that on random points, the VUF doesn't collide. And for the same point, but different keys, random points, the VUF also doesn't collide. And this, by the way, the second case we study specifically because it's the case of ECVRF that it's used on application. So along the way, we also prove that ECVRF is unbiasable in the non-programmable random oracle model. Okay. Next, we provide another compiler. We actually provide a new compiler in the standard model, compiling any VRF into a verifiable random bijection. I don't have a definition slides for it, but by bijection here I essentially mean that there should not be any collision. The function has to be injective, and essentially domain and codomain has to be of the same size. So our construction relies heavily on prime order groups, and actually that's an open question if you can remove this assumption. So first of all, we start with an input that is essentially a vector of field elements, just of length 2. We do a Pedersen hash. There was a typo. I think I thought I uploaded the slides. Anyway, so you do a Pedersen hash here. So you have essentially a matrix of 4 group elements in the public key, and you do a Pedersen hash of these 2 field elements with this matrix. So what you get eventually are 2 group elements. And then you compose this with 2 face-tail rounds. Okay, so just to break this construction into pieces, so why do we need all these components? So the 2 face-tail rounds is required because this is essentially, and the face-tail round is done, by the way, with the VRF. So the face-tail round is a bijection, and this is, I would say, at this point, a well-known fact. But the face-tail round alone, composed with the VRF, would never give you a VRF because of some issue that arise because you need to explain essentially the output at some point. And this breaks the security of the face-tail rounds that you are essentially using. So the idea here is that, so essentially we need to compose the 2 face-tail rounds with the Pedersen hash in order to avoid an attack on the face-tail rounds that essentially is asking to evaluate the second part on different input in the first component, but the same in the second one. So this Pedersen-Hash essentially is saying that the second it's hard to find two different vectors that map to the same value for the first component, and this gives you, this allows you to prove that this is a pseudo-random, this is a verifiable random function. And for bijection, two-phase round again, it's a bijection, and Pedersen-Hash, it's a certified bijection because you can check, for instance, with pairings that this matrix has non-zero determinant. So this is fine. Since it's a bijection, this is unbiasable. It's very easy to show that because the input you should evaluate this for unbiasability is a random input, so randomness should be preserved. But this is only fine when you have one verification keys. You have no way, up to this point, to ensure that two different verification keys doesn't give, for instance, correlated outputs. So to do that, essentially, we need somehow a way to produce random values out of your verification key and the random input you start with. So let's say we have, for instance, a verification key and our input vector x. So our generic construction works by splitting x into two parts. One is going to be a PRF key, and the other part is going to be some randomness we will use later. And in this simplified construction, what we do is that we generate many random points, one for each verification keys that are on the table, essentially, by evaluating the PRF on the key that is given by the inputs on the verification key that we started with. And to ensure pseudo-randomness, we also need to add a commitment so that this map essentially is an injective map. So this commitment has to be a statistical commitment to K and R so that there cannot be any collision up to this point. And then, using the same idea as before, we do a Pedersen-Hash, but this time is a shrinking one, and we compose this with the random bijection that I mentioned before. So now I'm lying a little bit because this Pedersen-Hash here would return group elements, and the verifiable random bijection I mentioned before started with field elements. But in the paper, there is a trick to actually avoid this issue that I'm not explaining here for simplicity. And finally, you get the output. And this can be proven to be unbiasable under the, assuming you have a group per D-log and PRF hard, even assuming preprocessing. So just to sum up, we basically essentially show that we have a new notion we call unbiasability that is enough for applications that were known, for instance, single leader election, that can be satisfied by construction that are actually deployed in practice, like ECVRF, and that can be generically achieved in the standard model without random oracles. There are also many open questions that we leave. One, for instance, is like, what are the minimal assumptions to achieve unbiasability? We heavily rely on the discrete logarithm assumption, but we don't believe this to be minimal. And also, we wonder if it's possible to have post-quantum construction of unbiasable VRF. For instance, based on lattice or isogeny or even hash functions, but we believe that to be harder. And finally, we wonder if there are like verifiable random bijection on a small domain, which is not the case in our construction because the group has to be, of course, of exponential. Has to be of exponential size for the log to be hard. So that's it for my presentation, and thank you for your attention.
Any question? Please use that microphone.
So I'm not sure, I came a few minutes late, but your notion of verifiable random bijection, it seems to be the same, but I'm not sure. Probably there is some difference from in Eurocrypt 07, we had a paper on verifiable random permutations, and our result was that you can generically, if you apply Feistel, but without a group structure, you can just take any verifiable unpredictable function, and then, security parameter rounds, you can just, so we show that anything less than security parameter rounds generically is insecure. There is a counterexample, but if you have security parameter rounds, you get a verifiable random permutation from, I was just curious, what is the connection, and if that would solve, for example, your post-quantum issues and so on.
Okay, so first of all, I actually saw the paper after all these submissions happened, so I'm sorry for that. But I did saw the paper where you have a non-constant number of Feistel round composition, if I'm right. And also I think you have some other assumptions on the VRF to satisfy. Like you need probably this collision resistance on XOR, I think. I don't remember precisely. We can discuss it offline.
We can discuss, yeah.
Yeah, totally. I mean, I'm not 100% sure, but I would say probably yes. This would, I mean, if that, I mean, I don't, I would say, I'm not sure on the restriction you have on the VRF, but if you can have the VRF satisfying your definition that are post-quantum, that would already solve the problem, I would say, yeah. So in this case, we do two-phase tail round also to minimize the number of calls, and two-phase tail was enough.
Oh, that's really nice if it works. That's really cool. It's just, yeah, I was just curious generically if there is, and also for your definition, is it enough for, there is this notion of simulatable VRFs. I don't know if you know, like by Melissa Chase, there are some papers about simulatable. Those notions, I think, are only satisfiable in an idealized model, but given that you anyway use idealized models, I don't know, is your definition of unbiasability, does it generalize to the simulatable VRFs, and you know, will the construction work?
Okay, so that's actually another problem I didn't mention in the slide, but that's another problem we leave like as often. I mean, another problem we leave. If we can have like, you ask, the question is like if you can have unbiasability and simulatability together.
At the same time, yeah.
We don't know. If there are generic combiners, that would be an interesting question, or if in general you can have any VRF that is both unbiasable and simulatable. Yeah. Thanks for the question.
Great work.
Thanks.
Hi, thanks for the nice talk. In the slide 9 again, for the same construction?
Which one?
The construction that you showed before.
The VRB.
Yeah. Here, what properties required from the Peterson hash?
So essentially, we do need only, actually, I mean, I'm also like simplifying a little. You only need essentially that this is a certified bijection. So it's, and this is the case in our, the version I'm presenting, because it's 4 group elements and free pairing, for instance. In a type 1 pairing group, like you can check the determinant to be 1, or at least non-zero. So you need this to be a bijection, and you also need it to be collision resistant on the second component.
So in principle, you could use some universal hash function.
I'm not sure, because I don't think you have computational, I mean, I don't think like collision resistance would be computational, right?
Would be information theoretic.
Yeah, but this is actually in the public keys sampled. So this is the issue comes from for essentially pseudo randomness, and this would be in the public key, and the input could be adaptively chosen after I see the universal hash function. I might be wrong, but I think like the argument would work maybe if you can sample the two things independently, input and universal hash function.
So okay, it's not key that Peterson hash.
At least we can discuss it offline if you want, but okay. Anyway, thanks for the question.
Any other question? Okay, so if not, let's thank the speaker again. So the next talk is pseudo-random isometries by Rita Gulati.
So hello everyone, I'm Aditya Gulati, and I'll present pseudo-random isometries, which is a framework to analyze pseudo-random primitives for in the quantum world. This is a joint work with Prabhanjan Anand, Fatih Kalioglu, and Yaoten Lin, all from UCSB. So classically, we know that we have a nice toolbox of pseudo-random primitives using which we can construct other crypto primitives. For a long time in the quantum world, this was open, like an analog for this was open. Recently, there has been a lot of work for this, and we give a systematic way to analyze all of these pseudo-random primitives in the quantum world. So even before discussing what pseudo-randomness looks like in the quantum world, let's see what randomness looks like in the quantum world. So it comes in 2 flavors. There's hard random states, which are states that look like they were picked at random on the block sphere. And there's hard random unitaries, which are unitaries that look like they were picked at random from the unitary group. Now, this second definition is not as satisfactory as the first. Hence, we work within a characteristic definition of this, which is defined as follows. It's called invariance. So if U was picked from the hard distribution, U is a unitary picked from the hard distribution, then if we multiply it on the left or the right with a fixed unitary, the resulting distribution is still hard. So this gives us another characteristic definition of hard random unitaries. So now that we know what randomness looks like, we can define what pseudo-randomness is. So it again comes in two flavors. There's states. So there's pseudo-random states, the study of which was started by JLS in 2018. And there's also pseudo-random function-like states, which were introduced in AQY in 2022. These are primitives that both behave like Haar random states. And then there's operations. These primitives try to behave like pseudo-random unitaries. These primitives try to behave like Haar random unitaries. We have two. One is pseudo-random unitaries, which was introduced by JLS in the same paper in 2018. And we got the first construction in 2024 in MPSY. And the other is pseudo-random state scramblers. These were introduced in 2023 in LQS+, and these behave like Haar random unitaries on T copies of the same input when it's queried selectively. So now that we have these primitives, are these useful? So in fact, we have seen a lot of applications of these, starting with in 2020, Kreshmer showed that pseudo-random states and unitaries are black box separated from one-way functions, giving us a new minimal assumption on which we can base crypto. And since then, we have had a lot of papers basing different a lot of crypto primitives on this new minimal assumption. There's also lower bound proofs in quantum ML using pseudo-random unitaries, and there's work on ADS-CFT and quantum gravity using pseudo-random unitaries. So these are useful, and all the definitions of these primitives look similar. So is there a way to systematically study all of these? Like, the definitions are similar, but till now, for all primitives, we have to check their pseudo-randomness case by case, and there's no systematic way yet. So in our paper, we introduced this framework called pseudo-random isometries, using which we can study all of these primitives. So our results are as follows. We define pseudo-random isometries as a framework to study other primitives. We define almost invariance, which is a technique to prove pseudo-randomness for all primitives, and we also characterize the exact properties needed for pseudo-randomness. We give a construction of PRIs from one-way functions, and then we show some applications, including length extension theorems of other pseudo-random primitives, quantum message authentication code, and multi-copy secure encryption schemes, and succinct quantum commitments. So what are pseudo-random isometries? We can, to define pseudo-random isometries, we need to start by defining what Haar random isometries are. So Haar random isometries are simply defined as follows. On your input, append a bunch of zeros and apply a unitary sample from the Haar distribution. And pseudo-random isometries are just efficiently implementable circuits that behave like Haar random isometries. So formally, we need two properties. We need efficient implementation, which means that there is some polysize circuit which implements an isometry that on the input psi of length n and on some key outputs an n plus m length qubit state using this isometry. And we call this an n plus m PRI. And the second property we need is Q security for some set of inputs Q. So we define it as follows. For any row for any quantum state row in this Q, we need T-parallel applications of the pseudo-random isometry Fk on rho to be computationally indistinguishable from T-parallel applications of a Haar random isometry on rho. And we call this an n plus m Q secure PRI. So how are these related to other primitives? So we can set different values of n, m, and q to see how pseudo-random isometries are related to other primitives. Hence, we call this a framework to analyze other primitives. So for example, if we set q equal to the all zero states, then a PRI secure on this q is a PRS. If we set q to be the set of all computational basis states, then the PRI secure on this set is a PRFS. If we set q to be the set of T tensor of the same state, then a PRI secure on this q is a PRSS. And if we set m equal to 0 and q equal to the set of all states, then this is a PRU. Interestingly, PRUs also imply PRIs in the strongest sense, which means PRUs imply PRIs for all n, m, and q. But we think that PRIs are a simpler primitive to build and hence can give us more interesting results with easier assumptions. Okay, so how do we actually analyze pseudo-randomness of PRIs and some other primitives? We start by the following intuition. The output of a pseudo-random primitive is maximally scrambled. Hence, applying a t-fold har on top of this should not change it much. Or the output should be invariant under t-fold har. And this, interestingly, this turns out to be the only characteristic property we need, which means that if the output of a pseudo-random primitive is invariant under t-fold har, then the pseudo-random primitive is secure. So formally, in case of pseudo-random isometries, it means the following. A pseudo-random isometry is Q secure for some set of inputs Q. If for all rho in Q, applying t-fold pseudo-random isometry on rho should be invariant under when we apply t-fold har on top of this output. So these two states need to be these two outputs need to be closed. Interestingly, this has already been used in a subsequent work in BM24 to prove pseudo-randomness of PRUs on some set of queries. And the proof of this is deceptively simple. It just uses two properties. One, we need har invariance, which means if U is sampled from the har distribution, then multiplying U with any fixed unitary V on left or on right still results in the har distribution, and that any isometry I can be written as the following: append a bunch of zeros, and apply a unitary on top. And just with these two properties, we can already see the proof. So the proof is as follows. So PRI is Q secure if rho, if T parallel applications of FK on rho is close to T parallel applications of the har isometry I on rho. Now the har isometry can be broken into appending a bunch of zeros and applying a har unitary on top. By invariance, we can write, we can pre-multiply this with any fixed unitary. In our case, we can pre-multiply it with UFK, which is the unitary part of our construction of the PRI. And now notice that appending a bunch of zeros and applying UFK is exactly the construction. So since we have only used equalities, for the first two states to be close is equivalent for the first and the last state to be close, which means that the PRI is secure if the output of the PRI is almost invariant under t-fold har. Okay, so now we have a nice property using which we can prove security, but can we characterize these almost invariant states? To do this, we first define permutation operations. So permutation operations for p-pi for pi in the symmetric group is defined as follows. It takes as input some t registers and permutes these t registers according to the permutation pi. So now using just this, we can completely characterize all states that are almost invariant under har. So rho is almost invariant under t-fold har if and only if rho can be written as rho is close to some linear combination of permutation operators. This gives us a very nice property because to prove pseudo-randomness of any primitive, we just need to show that the output of the pseudo-random primitive is close to a linear combination of permutation operations on all possible inputs. So this gives a very clean result on how we can prove pseudo-randomness of primitives. So now that we have a theory on how to prove pseudo-randomness, can we construct PRI from a good assumption, for example, one-way functions? In our paper, we propose the following construction. On the input, append a bunch of zeros, apply a Hadamard on these zeros, followed by a random function, which is instantiated by a QPRF, and a random permutation, which is instantiated by QPRP. And this is the construction. And we show that this construction is secure against computational basis queries, which means that it's a PRFS, is also secure against T-tensor of the same pure state, so it's a PRSS, and is also secure against HAR queries, which I'll define in the following slides and is useful for applications. And we conjectured that this is secure against Q for all states Q. And this conjecture was resolved in 2024 by MPSY, which showed that this is indeed secure against all possible states. Okay, so now we move on to applications. The first application we show is length extension of other pseudo-random primitives. For this, we need to understand what HAR queries are. So HAR queries are defined as follows. We sample some polynomially many different states from the HAR distribution, and we apply the PRI construction on top of these states. We also give polynomially many copies of all of these states in the clear. And we need this to be, the PRI to look pseudo-random on top of on these states. And using this, we can prove some length extension theorems. So we can show that a HAR-secure n plus m PRI can extend the length of an n PRS to an n plus m PRS, and also a HAR-secure n plus m PRI can extend the length of an n qubit PRFS to an n plus m qubit PRFS. In general, we don't have a technique of extending the length of pseudo-random primitives before, so this is a novel result which should have applications further too. And apart from this, we also show some other applications. We show quantum message authentication codes. We show multi-copy secure encryption schemes and succinct quantum commitments. So in the classical setting, message authentication codes are defined as follows. So there's two parties, a challenger and an adversary. The adversary sends a bunch of inputs to the challenger. The challenger then sends a signature of all of these inputs back to the adversary, and the adversary has to send a new input along with a forged signature that needs to pass the verification, where this x star has to be not equal to all of these x1 to xt. Now, ideally, in the quantum case, we want to replace the inputs with quantum states. But this, in general, is not possible for the following reason. First, the definition of not being equal to is hard, because you can always output a close enough state for which this previous signature just passes. And if we want the new state to be orthogonal, then we somehow need to check that the state that the adversary is outputting is actually orthogonal to the initial states. But this is hard too, because checking this would destroy the state. Hence, this definition seems unachievable. We work in two separate settings because of this. The first setting we define is as follows. The adversary has to output T copies of the new message as well as the forged signature. And we run swap tests on these. And this can give us exponential security. We show how to instantiate this with PRIs. And the second, we just need the adversary to output T copies of the forged copies of the new message, as well as only one copy of the forged signature. And we run permutation tests on these, and we can get inverse polysecurity for this. Apart from this, we also give some other applications. We show multi-copy secure encryption schemes, where we use similar techniques similar to the PRSS paper to get multi-copy secure encryption schemes. And We also give succinct quantum commitments where we use techniques similar to those used for PRUs and show that those can be applied to PRIs to get succinct quantum commitments too. So to summarize, we define PRIs and we show that they're related to other pseudorandom primitives. We give a new technique to prove pseudorandomness for PRIs and other quantum primitives and completely characterize these states or this needed for this proof technique. And we also give a construction of PRIs from one-way functions, and we show a bunch of applications, including length extension theorems, quantum max, multi-copy secure encryption schemes, and succinct quantum commitments. Thank you for your attention.
Any question?
A short announcement. We invite the third speaker to go to the back to get the microphone.
Thanks a lot for the talk. So first of all, for PRUs, what you're considering is just parallel query security. Right?
Yeah,
like
just
the original definition of PRUs is considers adaptive query access to the
Yeah, that's true. So we only consider selective query security. When we published the paper, there were no constructions of PRUs yet either, and so it seemed like a very hard problem to think of adaptive queries yet. So we considered only selective queries and showed that just selective queries is also enough to get a lot of other applications. So yeah.
Yeah, that makes sense. So at some point, just one more question, if it's okay. At some point, you made this remark that you can get any type of PRI from PRUs, like PRIs for any N and M from PRUs.
Yeah.
You don't need to. I'm kind of interested in this fact because don't you need like some kind of compatibility of the dimensions?
So given a PRU, so the way PRUs are defined, they are defined for all possible input lengths. When you define it as a family. And so given an n plus m length PRU, you can get an n plus m PRI by just fixing a bunch of fixing some inputs to be 0 and just passing the input on the rest of.
Ah, I see.
Yeah.
Because I see. I understand.
Okay, thank you. Yeah.
I have one single quick question. You said that you extend your research to the almost every quantum state. Is it about the non-adaptive security or adaptive security?
We only show this for adaptive security, non-adaptive security, but I think there should be a way to get adaptive security to get this. Yeah, PRUs should imply this in the adaptive setting as well, I think. Yeah.
Okay, thank you.
Yeah.
Any other question? Okay, if not, let's thank the speaker again. So the last talk is direct PRF construction from Kolmogorov complexity by Yan-Yi Liu. So. Okay, please.
Thank you for the introduction. And hi, everyone. This is a joint work with Professor Rafael Pass at Tel Aviv University and Cornell Tech. Let me start off by introducing the connection between Kolmogorov complexity and cryptography. In a very recent work, we showed a characterization of one function through the notion of Kolmogorov complexity. And we show that when functions, and thus almost all private key primitives exist, if and only if computing the time-bounded Kolmogorov complexity is mildly hard on average. So what is Kolmogorov complexity? So this is basically the question we're given a string x, and we want to compute like the length of the shortest program that computes the string x. And here we consider the time-bounded version where we just focus our attention to efficient machines. And this is, of course, like a very classical notion and has been studied since basically the 60s. And so today, as we can see, this result is kind of rather theoretical. And today our focus is going to be more on the practical side. Okay, disclaimer is more on like the theoretical, practical side. And the purpose of this talk is to convince you that this can be made practical. Okay, so if we want to focus on like theoretical, practical sides, and we know there is like a really nice object we should look at, namely pseudorandom functions. Pseudorandom functions are really like central objects of private key crypto. And if you think about it, it's really like the Swiss Army knife if you want to do practical crypto. So it leads to very simple construction of private key encryption, messenger authentication codes, and also identification schemes. And those are like crypto schemes that's kind of widely used on the internet. And besides this, PRFs have also found applications in resetable security of this RAM and outside crypto, natural proof barrier, and also computational learning theory. So let me very quickly introduce the notion of PRFs, introduced by Godawasa and Mikali in 1984. So like a PRF is like a family of function indexed by like a string z, or we can see like a seed z. And we say that f is a PRF if it's efficient, so given the index and z and the input x, the output of PRF should be computed in polynomial time, and it's also pseudorandom. Namely, the output of a PRF should be indistinguishable from the output of a random function in the eyes of efficient machines. And let me mention that we consider adversarially and adaptively chosen inputs. And super importantly, today I'm going to focus on quasi-polynomial security. This means that PRFs that are secure with respect to like t time attacker, where t is 2 to the power of c times log square n. And super importantly, like the exponents of my quasi-polynomial function over the log n term is fixed to be 2. So it's always like some 2 to the power of some constant c times log square n. Okay, as mentioned, PRFs are like super important objects in crypto, and there are many constructions of PRFs. And we know we have the so-called generic construction where you start from one function, you transform it into a PRG, and then you get like a PRF using the GDM tree construction. And we also have the heuristic construction, AES, which is arguably like the most widely deployed PRF. And we have constructions from DDH assumption, factoring assumption, and also lattice assumption. However, we're not really very satisfied with them. So for the generic construction, unfortunately, it's like too inefficient, and it's like adds something like an n to the 4 overhead to the PRF you get. And the AES, no proof of security. And for the DDH-based construction and factoring-based construction, we know it's broken like by like a quantum computer. And for the lattice assumption, we don't really know, but well, there's at least some attempts. Okay, so today, I'm going to show you like a direct construction of PRF from time-bounded Kolmogorov complexity. And before I tell you what the result really is, let me mention that, well, the assumption we need in our construction is equivalent to the existence of quasi-polynomial wave function, and we get like a quasi-polynomial secure PRF out of the assumption. So this is the direct PRF construction from like a natural minimal assumption that is kind of also like both necessary and sufficient. So if you break like the candidate we have today, you have to break like all PRF candidates. Okay, so before I tell you what the result is, let me quickly introduce the notion of time-bounded Kolmogorov complexity. And here we really consider this like truth table compression problem. So think of like the input as like a truth table of the some function, and the question here is like, what is the smallest program that computes the truth table? And by computing the truth table, I mean like here is the truth table, and you want to find a program such that on input 1 it outputs the first bit of the truth table, and on input 2 it outputs the second bit. And my program here are time-bounded Turing machines, and we get this so-called local compression version of T-time-bounded Kolmogorov complexity. And in more detail, we fix like a runtime bound T. Think of T just as like n squared. And for any string x, we define the quantity k superscript T of x to be the length of the shortest program computing this truth table within, say, time length of pi square. And more formally, we need to fix a universal Turing machine U to tell us how to interpret a string as a program. And for our results, like the choice of universal Turing machine doesn't really matter. But if we want to deploy it in practice, it does really matter. I want to mention here that we can just think of like the canonical universal Turing machine, where a Turing machine has like a huge transit function and a bunch of tapes and like a head on each tape. And so if we just given a universal Turing machine, and we also need to fix like a running time bound, and basically we can define kt of x just as above. And now let me define the language mktps, where t is again the runtime bound, and s is like a threshold function. And this language contains like all truth tables such that its kt capacity is at most s. And let me proceed to like the average case hardness we need for this language. And here's like a simple observation. So if like the threshold is say n/2, then my mktps language is like super sparse. So think of it actually defines, like a function that takes like a program of n/2 bits, and it outputs some like a truth table of n bits. And if you think about it, there are kind of many like outputs which doesn't have an input to it. So like my language is going to be super sparse, meaning that this language is like trivially easy on average if the distribution is uniform. You just say no, there's no program computing it. So to deal with this issue, our solution is to instead require hardness conditioned on both yes and no instances. So we say that some algorithm succeeds on like deciding mktps if it succeeds on like at least a large fraction over yes instances, and simultaneously succeeds on a large fraction of no instances. So as you can see, this like outputting no heuristic is no longer deemed as a success. And we can define like the average case hardness, namely the language mktp doesn't have such a heuristic. And now let me proceed to like the results. So before I state the results, let me tell you what assumption I need in this result. So my assumption is going to be, well, just the second bullet of this theorem. So this bullet says that consider some like runtime bounds, say like a linear or like an n square, like mktp with the threshold s be 2 to the power of all of square root n. So this is basically the language where given like a truth table, and you need to decide whether like there's a program of size s computes it or not. And my threshold function, if you stare at it, you'll notice that this is the inverse of my quasi-polynomial function. So mktp with threshold inverse quasi-polynomial, and we ask this language to be a hard-on average with respect to n-cube time attackers. So no n-cube time attacker can succeed simultaneously on a large fraction of yes and a large fraction of no. And as mentioned before, or you can see from this theorem, the assumption I need is equivalent to quasi-polynomial one functions, and in turn equivalent to quasi-polynomial PRGs, PRFs. And so our main theorem basically says that from exactly the same assumption, we get like a direct construction of quasi-polynomial secure PRF. So this is basically our result. And a couple of remarks are in order. So this is the first construction of a PRF from like a nature hardness assumption that is like both sufficient and necessary. And second, as you might notice, our PRF only has like on security parameter lambda only has input length log square lambda. This is sufficient for example, CPS secure encryption. If we want to get like an epsilon to the lambda to the epsilon input length, we can either consider like a much smaller threshold, namely threshold being like polylog n, or we can use like standard domain extension technique to get its like a large input length. And one thing to notice, we get like n-cube hardness implies quasi-polynomial PRFs. This phenomenon has been observed in prior work. It's called like hardness magnification. And let's talk about security and efficiency. And think of t, the runtime bound in my mktp, to be linear. And think about this like error parameter I never mentioned to be like 0.1. Our PRF has running time basically lambda to the 1.1, and has seed length basically lambda to the 1.1, ignoring polylog lambda factor. So at least our PRF has like pretty good asymptotic efficiency. And to compare it with existing constructions, let me just say the conclusion here. Basically, all constructions except the LWE one and the generic one have roughly the same efficiency. Ours is like a 0.1 worse in the exponent. So let me give like a construction overview. Our construction relies on LP21 function and the so-called Nielsen-Williamson generators. And let me sketch the construction. So to get like a PRF, in step 1, as mentioned, we rely on the so-called LP21 function. So we use like the seed of the PRF to sample like a random index j from 1 all the way to my security parameter lambda. And I use the seed to sample like a random program. As mentioned, think of like a canonical Turing machine of length j. And I define the running time of my program to be like lambda square. Okay, so this, I have like a program. And the next step is to define like a function. Basically, I let f to be the function that's computed by this program. And the input length to my function is basically log square lambda. Recall that our PRF will have roughly like log square lambda input length. Okay, so first step, pick like a random index and a random program and define like a function that's computed by the program. And in step 2, we're going to use Nielsen-Williamson generator. Nielsen-Williamson generator is like parameterized by, as mentioned, the function f, and also it has a seed y. We can pick y like from the PRF seed, and it comes with a bunch of like pre-processed subsets, namely S1, S2, all the way to Sm, and we have like quasi-polynomially many such sets. And for example, say here S1 is like 147, and how do I compute like my generator? So, for example, my seed y here is like it's a 9-bit seed. It's like y1 all the way to y9. And to compute the first bits of the outputs of my generator, like I look at S1, which is 147, and I take like a y1, y4, and y7 together, and I concatenate them together, and view this as the input to my function f. So basically, we run the random program on this concatenated inputs, and this program will output 1 bit, and this is going to be the first bit of my generator. So it's kind of, if you look at this, it's like quite simple. You just like do kind of a projection over coordinates, and you compute the function f, which is just simulates the random program for like lambda square steps. And you do this for the second bit and the third bit, and so on. So this is like the output of the Nielsen-Williamson generator. And there's like one step in which we do like a security amplification where you just take like some fresh repetitions and you do an XOR. So let's look at the efficiency. So notice that the output of Nielsen-Williamson is like quite efficient. Namely, like each output bit only involves like evaluating the random program once. And you can see it's actually like a PRF rather than a PRG. And although like we need like some certain amount of like repetition, and let's just kind of ignore that. And the security here will basically show that any attacker that breaking my PRF can be used to build like an attacker that breaks my MKTP language that has been mentioned before. And I won't go too much go into the security proof. Please refer to the paper for the proof. And very quickly mention that Nielsen-Williamson is like an object used in randomization, and there are like a lot of difference. And I want to mention that our results is kind of the first result which like utilizes the security proof of Nielsen-Williamson in cryptography. And let me wrap up very quickly. So we present like a direct PRF construction from like a hardness assumption that is both sufficient and necessary. And this is like first PRF based on like a concrete, such a concrete assumption. And let me use like the last 1 minute to kind of sketch a little bit that our result opens up like the possibility for like building like a practical PRF construction from like a minimal assumption. So towards like a practical security, like the question is like which security parameter we want to run this in practice, or like where is the security stems from? And we here propose the so-called like a meta complexity challenge, where you use like 1,000 bits, or you like use like 5,000 bits. You pick like a random canonical Turing machine, Or you can pick like a random circuit. It's can roughly the same, it's not the same thing, but you can, if Turing machine is too hard, just think of like a random circuit. And you basically output the truth table of this circuit. And the challenge here is to output the compression of this truth table using like a little bit more bits. And this is closely related to the so-called like Hutter price, which requires compress like the first gigabytes of Wikipedia. This is kind of compressing human knowledge. And this is like a general attack to my challenge, which is like a gzip. And so basically, we rely on hardness of compression, and compression is like not really a new thing here. Compression is kind of has been there for like many years. Finally, let me remark that this suffices to give a PRG, but to give a PRF, we need something like a little bit more. And thank you for your listening, and I'm happy to take questions.
Any question?
Hello, thank you for the talk. Just a very naive question, maybe. Sometimes, like in the algorithm, you sample a random program,
yes,
which have a bounded complexity.
Yes.
But the question is, okay, how do you do that? Because I guess you could just sample, you can do that? Sample a program?
Well, if you want to sample a circuit, right? Then there's no like a circuit just evaluates it is like very efficient. And if you want to do like a Turing machine, you kind of want to stop at like a lambda square or of lambda steps, and that's the only thing
so
you need.
Just okay, you
just stop.
Okay, machine, and you just say okay at this. Okay.
Yeah,
thank you.
yeah.
Thank you very much.
Hi, thanks. I was wondering, I think you wrote it even in the paper, but I didn't get to that point yet. The Nissen-Richardson generator usually assumes that the evaluator has more runtime than the distinguisher, right? Do you have a nice, like, succinct description on why this is not a problem here?
I guess a one-sentence answer to that is like we rely on like a particular average case hardness, and this is average case hardness from like a particular function based on MKTP. Which kind of get rid of this issue.
Okay, thanks.
Yeah.
Any other question? So, for example, if you want to construct a commitment, PRG is enough.
Yes.
So, is there any direct construction of PRG, not PRF? I might say I might be missing something, but if you have a PRF, then it's kind of also like a PRG. Yeah, of course. But if your goal is a PRG, can you construct PRG more efficiently?
Our construction is like almost it's like lambda to the 1.1, so it's kind of morally it's like almost linear, so it's kind of very efficient and. Yeah, to get a PRG, we might start from like MKTP with like a larger threshold. So here, like my threshold is like this weird 2 to the power of square root log n. You think about it, it's like tiny. So if we just want a PRG, something like a square root n should work. Yeah, but the PRG wouldn't be more efficient. So you can first morally start from like a weaker hardness assumption.
So if not, let's thank the speaker again. Okay, so this is the end of this session.